So here's an example of a problem where algebraic simplification is necessary because we're not just finding the formula for f prime, we actually want to answer a question about it. We want to know the values of x that make f prime of x equal 0. And remember, f prime of x measures the slope of f, and so if we're trying to figure out when f prime is 0, that means we're trying to figure out where f has a slope of 0. And so often in the book and on the course, you'll see that question asked as, where does this function have a horizontal tangent line? Because a horizontal tangent line means a slope of 0. So first let's find the derivative. We recognize this is a quotient, and so we know we need the quotient rule. And like before, I'm going to think of my numerator as being my box, my denominator as being my circle, and I'm first going to just write down what the quotient rule says to do. The quotient rule says to copy the denominator multiplied by the derivative of the numerator. Again, I'm not doing it, I'm just writing down that I'm going to do it. Minus the numerator times the derivative of the denominator. So again, I'm not going to do that, I'm just going to write down the derivative of the denominator. And then the denominator of the derivative will be the square of the original denominator. So I need to actually do the derivatives that I wrote down. The first one up there, I'm not even going to flatter by putting parentheses around this because I can see that it's x squared plus 169 times 1. The derivative of x is 1. So I know that that's multiplied by 1, which means that there's just nothing there. And then I'll have x times, and the derivative of x squared plus 169 is just 2x. And then I have the same denominator, x squared plus 169 squared. So to figure out where this is equal to 0, I do need to remember one fact about fractions, and that is that the only fraction you could ever have that's equal to 0 is if the numerator is equal to 0. That's the only way that can happen. And so if you're trying to figure out for what values of x this is true, then you're really just asking for what values of x, and I'll go ahead and multiply x times 2x here and get 2x squared. You're really just solving this equation. You're figuring out where the numerator is equal to 0. So even though there's a fraction in the answer here, it doesn't really make the algebra hard, because since we're trying to find where the fraction is 0, we're really just trying to find out where the numerator is 0. So I'll just do that over here. I have x squared minus 2x squared, so that means I have 169 minus x squared equal to 0. And I know that when I'm solving a polynomial equation, I want to try to factor. This was one of the reasons we did the factor FOIL review. This is a special kind of factoring because the outer and inner terms aren't there. There is no outer and inner term, so that means they must have canceled out. So I will have a plus x and a minus x. That'll give me the minus x squared. 169 is 13 squared. So that means if I put 13 here and 13 here, then 13 times 13 is 169, but the outer and inner terms from FOIL are both going to be, well, one's going to be 13x, one's going to be minus 13x. So they go away, they cancel each other out. So this is the correct factored form, and so that means my answer is that either 13 plus x is 0, which means x is minus 13, or 13 minus x equals 0, which means that x is positive 13. So plus or minus, x being minus 13 or plus 13 is going to be the final answer to that question. The last example, there's only one of them in this assignment, and I'm really trying to get you just to think about the fact that these rules really don't compute derivatives by themselves. What the rules really do is break a derivative problem into simpler derivative problems. In the examples we've seen so far, the simpler derivative problem was just one that we could just get the answer to. We didn't have to do any extra work. This is an example of a problem where we're just going to break down a complicated derivative problem into a simpler one. And we keep doing that until it's something that we know how to do. So I see this and I think immediately quotient rule, because I see a quotient. And the key is not to look too closely. don't worry about what the numerator and denominator are. It doesn't matter what they are. The quotient rule will still apply. So the derivative here will be the denominator times the derivative of the numerator. And you start to see why I'm in the habit of not trying to do that in my head. That's not easy. But I'm not going to worry about it because I'm not really trying to do it at this point. I'm just writing down that that's what needs to be done. Then the numerator times the derivative of the denominator. And at least they made one part of this problem easy, and that is that the denominator is e to the t, so the derivative of that's going to be e to the t. So that's an easy one. But, oh, and I do need my denominator here, so the quotient rule is not done yet. It has to be over e to the t squared. Now, this part is easy. We know this part here is just e to the t, so that's no problem at all. But then we see this thing, this piece, and we realize that that's fairly complicated. But I did not try to do it in my head as I wrote it down. So what I can do is just come over here and ask myself, well, what is 5t to the 6th? I'll just do it on scratch paper or over on the side of my page. What is this derivative? Well, if you look at it, that's a product rule problem. If I put a box around this part and a circle around this part, then this looks just like the product rule, a box times a circle. And so I know when that happens that I just have each thing times the derivative of the other. So I'll have the 5t to the 6th times the derivative of log t plus, sorry, I did not plan spacing very well here, but plus log t times 5t to the 6th prime, the derivative of 5t to the 6th. So now I can actually do each of those derivatives, and now these aren't too bad. This is 5t to the 6th, and the derivative of log t. Remember, we don't care for log so much maybe, but the derivatives are easy. The derivative of log t is 1 over t. And that t in denominator is going to cancel with one of those t's in that 5t to the 6th expression, which will make life easier when we simplify. Plus log t, and then the derivative of 5t to the 6th is 5 times 6t to the 5th. I'm using the power rule there. So I'm running out of room here, but I'll just write the final answer for that. That's 30t to the 5th will be the derivative of 5t to the 6th. And you should just check that if you don't quite see where the 30 comes from. Do the steps and you'll see where I got that. So I'll go ahead and simplify this because I know I'm going to have to simplify the whole thing. 5t to the 6th times 1 over t is going to be 5t to the 5th plus 30t to the 5th log t. When I copy that from here over to here, I'll try to do it more carefully. So in my derivative, this one is pretty complicated, but we didn't have more complicated rules. We just had to use our rules more than one time. So I have my e to the t times the answer that I got for the derivative of 5t to the 6th log t, which was 5t to the 5th plus 30t to the 5th log of t minus, now I have all this part, 5t to the 6th log t times the derivative of e to the t is just e to the t. And that's going to be divided by e to the t squared. So just about the only simplification you can do here is similar to the problem we did earlier where the e to the t that's here and this e to the t could be factored out and canceled with one of these e to the t's. So if I do that, if I factor out an e to the t from the whole numerator, I'll have 5t to the 5th plus 30t to the 5th log t minus 5t to the 6th log t. So that's what my numerator looks like. The denominator is log of e to the t times e to the t squared. So that's essentially e to the t times e to the t, and that's why I can cancel out one of those. So this is our best simplified answer, would be this stuff over e to the t. You can see the answer is not simple, but the point of having to do one problem like this is that these rules don't just do everything for us in one step, but by repeatedly generating the rules, we can eventually get the derivative of just about anything.